Hello Bobcats. In this video we will be discussing empirical and molecular formula determination. Now remember, the empirical formula for a compound really tells us the relative number of atoms of each element in the compound. Now this is also understood as the ratio of moles of each element in the compound. Remember from the discussion on moles and mole conversions that if you have a molecule, you can divide that into also moles of each element. For example, let's take calcium chloride. We know that calcium chloride has a mole ratio of 1 mole of calcium to 2 moles of chlorine. So there's a mole-mole ratio of elements. So it's not just about each atom, but we can also think of it as mole ratios. And if it's really about mole ratios, if you can determine the moles of each element, if you can determine the moles of each element, in a compound, you can therefore determine the empirical formula. Now, if you remember, we can, if we have the mass of something, we can take that mass. If we have the mass of something, we can take the mass to the mole. And so if we have the mass of each of the elements in a compound, we can go to the mole. Now, you'll have to remember back to chapter 2 when we talked about the law of definite proportion, and that compounds are made up of the percent by mass of each element. Well, we can use that idea to determine empirical formulas. So let's take a look at that. Let's take a look at an example where we're using percent by mass or definite composition to determine empirical formulas. So let's do the example here. Let me write it out. Example. Let's say we have a certain compound is found to have, oops, yeah, I'm having trouble writing here, is found to have 73.9% mercury and 26.1% chlorine by mass. So percent composition there. What would be the empirical formula of this compound? Now remember, this is percent by mass. So in order to get mass, this is percentage, in order to get mass so that we can convert to the mole, we can assume that that 73.9% mercury would be 73.9 grams of mercury out of a 100 gram sample. So if we have percent composition of a compound, we can say that that is 73.9 grams of mercury and 26.1 grams of chlorine, because remember, this is by mass. So now we can take those masses and convert the mass to the mole. So I have 73.9 grams of mercury, and I'm going to go to the mole, and the way I do that is convert using molar mass. So we know that 1 mole of mercury has a molar mass, so I go to the periodic table, and I have mercury right here, so it's 200.59. So I have a molar mass, or 1 mole is 200.59 grams of mercury. Grams cancel, so now I've got the moles, so that's 0.368 moles of mercury. So now I have moles of mercury. And then the 26.1 grams of chlorine. Let's convert the grams mass to the mole using molar mass. So 1 mole of chlorine is 35.45 grams of chlorine. So now I have 0.736 moles of chlorine. Now, if I were to use that as a ratio of each element, we could write it as, say, Hg, that's mercury, and then as subscript is 0.368, and chlorine with a subscript of 0.736, that's a mole ratio. The problem is we can't have fractions of atoms. So how do I convert these ratios to whole numbers? Well, what you do is you divide by the lowest value. So when I divide by the lower value here, the lowest one, 0.368, and divide this by 0.368 moles, then we realize that this is equal to 1, so we have Hg1, and then chlorine, when I divide 0.736 divided by 3.68, my chlorine is 2, so I have a ratio of 1 to 2 moles. And we could therefore write the compound formula as HgCl2. That's the empirical formula. So that's essentially how we get empirical formulas. So let's practice. This was an example. Let's do a practice to determine empirical formula again. So the next part is a practice. And so let's write out a practice problem here. Ascorbic acid which is known as vitamin C, has a percent composition of 40.92% carbon, um, 4.58% hydrogen, and 54.5% oxygen. Determine the empirical formula. Did I spell that right? Yeah. Okay. So remember, if we have percent composition, we can take percent and say that that's really 40.92 grams of 100. So I can say that I have 40.92 grams of carbon, and I'm going to convert the carbon to the mole. using molar mass. So 1 mole of carbon has a mass of 12.01 grams. Remember, we get that from the periodic table. So this comes out to be 3.407 moles of carbon. And the next one, we have 4.58 grams, 4.58 grams of hydrogen. Take it to the mole, go to the mole using molar mass, because we're going to compare mole ratios. That's 1.01 grams of hydrogen. So that comes out to be 4.535 moles of hydrogen. And then we have 54.50% oxygen, which we can say is 54.50 grams of oxygen. Take it to the mole, so 1 mole of oxygen is 16.00 grams of oxygen. And this is going to be 3.406 moles of oxygen. Now, so I have a 3.407 to 4.535 to 3.406 mole ratio of each element. But remember, we need whole number ratios, and to get a whole number ratio, I'm going to divide by the smallest mole value. So the smallest one is this, and so I'm really going to divide 3.406 moles, then I'm going to divide by 3.406 mole, and I'm going to divide here by 3.406 moles. Now I'm doing this so that we know that the moles cancel. So now I'm really looking at this. When I divide these two, I really get 1 carbon. Now this, when I divide it, I get 1.33 hydrogens, and when I divide this, I get 1 oxygen. Well, now I have a problem still. I still don't have a whole number, and we really can't round. If you have anything like 1.2 or higher, you have to multiply by a number to get it to a whole number. So, but if I have like a 1.1, I can round it, or 1.05, I can round it down to the whole number. Or if I have 1.95, I can round it up to a whole number. But in this case, I would say if I'm between 0.2 and 0.8, I need to multiply it by a value to get to a whole number. In this case, this is a third. So I can multiply a third by 3 and get a whole number. But that means I need to multiply all 3 of them by 3. So I'm going to go times 3, times 3, times 3. So this will be 3 carbons, 4 hydrogens, and 3 oxygens. So my empirical formula is equal to C3H4O3. That's my empirical formula. And again, so what we do in this is if you have a percent, now if you have masses, just use the mass. But if you have a percent composition, which is, remember, going back to a law of definite proportions, if we have percent composition, then you take and assume that's going to be grams out of 100, so 40.9 grams. So you take the grams to the mole using molar mass. Grams to moles using molar mass. Once you know the mole ratios, you got to get a whole number. So you divide by the smallest mole value. And in most cases, you'll get a whole number. But sometimes you'll get a number like 1.33. That's a third, and to take a third up to a whole number, we just multiply by 3, but you have to multiply all of it by 3. And remember, anything between 0.2 and 0.8, you have to multiply. Like if it's 1.2, you multiply by 5 to get to a whole number. If it's 1.25, you multiply by 4. But if it's like 1.1 or 1.05, you round it down. If it's like 1.9 or 1.95, you round it up. So now we got the empirical formula. Once we have the empirical formula, we can do molecular formula determination. So let's talk about molecular formula determination. Now, molecular formula determination, we need to understand that really a molecular formula is equal to the empirical formula times some whole number value, or a whole number multiple times n. Okay, that's a whole number multiple. So let's say I had an empirical formula of CH, and I multiplied it by 6, then my molecular formula would be C6H6. So the molecular formula is the empirical formula times a whole number multiple. Now, let me put this, because this is kind of an important concept here. Let's put a square around it. And to determine, or where, we can say where n, this value n over here, is a whole number multiple that can be determined by the following formula, where n is equal to MFM. Now MFM is molecular formula mass, the molar mass of the molecule, and EFM is the empirical formula mass, or the molar mass of the empirical formula. So MFM is molecular formula mass, and EFM is empirical formula mass. And you will always be given the molecular formula mass in the problem, and it will always be the larger number. So let's do an example problem here, and actually we're going to finish off the ascorbic acid and figure out the molecular formula for the empirical formula of ascorbic acid. So example. It was determined that the molar mass of ascorbic acid and remember, we just determined the empirical formula of ascorbic acid up here, but now is determined that the molecular mass or molar mass of the molecule is 176 grams per mole. So that is the molar mass of the molecule, or molecular formula mass. Now we need to determine the molecular formula. Okay, so remember, we have to find EFM, or empirical formula mass. So empirical formula mass, and I'm going to write it here as the EFM, that's the empirical formula mass of ascorbic acid C3H4 C3H4, remember this up here, C3H4O3, that is 3 times 12.01 plus 4 times 1.01 plus 3 times 16.00. This is equal to 88, and since this is a whole number here, I'm just going to leave this as a whole number. It's 88.07. We'll round it to 88.1. We'll get that close. It's really not that critical. Now, so that's the molar mass of the empirical formula, which we call the empirical formula mass. Now, remember, we're going to use this equation to figure out the whole number multiple. So N is equal to the molecular formula mass, MFM over EFM. Now remember, MFM is this value right here, the molecular formula mass. So I'm going to put 176 over 88.1. And when you divide that, it comes out to be like 2.0008. So this will be a whole number of 2. So all we do then is, remember, we're going to take, it's just, N is this value here, so we're going to take 2 times the empirical formula. And so that would be, if I wrote this out, we would say C3H4O3 times 2, which is equal to C6H8O6. C6H8O6, and that is my molecular formula. So again, a molecular formula is the empirical formula times a whole number multiple. We can determine that whole number multiple from the molecular formula mass, or the molar mass of the molecule, which is always given to you, and it's the bigger number, divided by the empirical formula mass. That's the molar mass of the empirical formula. So in this case, we know that the ascorbic acid molar mass of the molecule is 176 grams per mole. We have to figure out the empirical formula mass, which I did here, so that's 88.1, and then I'm going to use this equation to figure out N, which is molecular formula mass over empirical formula mass. 176 divided by 88.1, it comes out to be 2. And so really, it's empirical formula times 2, so that's C6H8O6. That's the molecular formula. Now we're going to do one more practice problem and kind of do it all in one problem as a review, and then we'll be done with this video. So one more problem, and then this video is done. Okay. So ethylene glycol which has, and it's the substance that's used in automobile antifreeze, so it's antifreeze. Ethylene glycol is composed of 38.1% carbon by mass, 9.7% hydrogen by mass, or percent composition is what we're doing, and 51.6% oxygen by mass. Now, it has been determined that the molar mass, so its molar mass is, molar mass, I kind of misspelled that, sorry. Its molar mass, getting ahead of myself there, its molar mass is 62.1 grams per mole. Okay, so that's the molar mass of the compound. So what we need to do is determine the empirical and molecular formulas. So the first one we're going to do is we're going to do the empirical formula. And with the empirical formula, remember, we're going to take the 38.1%, make it grams, so it's going to be 38.1 grams of carbon, and we're going to convert grams to the mole, because we're going to compare mole-mole ratios. So carbon is 12.01 grams of carbon, and that is going to be 3.21 moles of carbon. Then we have 9.7% hydrogen, and we'll say that's 9.7 grams of hydrogen. Convert it to the mole using molar mass. So 1 mole of hydrogen is 1.01 grams of hydrogen, and that comes out to be 9.60 moles of hydrogen. And then the last one was oxygen at 51.6%, so that's 51.6 grams of oxygen. So 1 mole of oxygen is 16.00 grams of oxygen, and that comes out to be 3.23 moles of oxygen. Okay, so I'm going to divide by the smallest. These are ratios of moles, but they're not whole numbers. So I got to get those ratios to whole numbers, and in this case what I need to do is divide by the smallest value. So that's going to be 3.21. And remember, I'm also dividing by moles to get rid of moles, but I'm not showing that. 3.21. So what this comes out to be is 1 carbon, 3 hydrogens, and then this is like 1.001 or 002, but it still rounds up to a whole number of 1 oxygen. So now I have 3 whole numbers. So my empirical formula is CH3O. That's the empirical formula. So now I've determined my empirical formula. I have to determine the molecular formula in this case, and so remember, to do the molecular formula we have to figure out the whole number multiple. And so the first thing we have to do is we need to determine the empirical formula value, empirical formula mass, or EFM. So the EFM for CH3O is equal to 1 times 12.01 plus 3 times 1.01 plus 1 times 16. And so this comes out to be 31.0 grams per mole is the molar mass of the empirical formula, or the empirical formula mass. We already know that the molecular formula mass, that was given, that's this right up here, 62.1. So that's 62.1 grams per mole. And next is we got to determine N. So the whole number multiple is going to be the molecular formula mass divided by the empirical formula mass, and that will be 62.1 divided by 31.0. That's essentially 2. I mean, it's like 2.008, but essentially 2. And so what we have to do now is we take the empirical formula and multiply it by 2. So my molecular formula is C2H6O2. I just took the empirical formula, multiplied it by this N2 whole number here, and I get C2H6. And that is the whole problem on how to figure out empirical and molecular formulas. And we will stop this video at this point. Have a good day.